From yesterday, I want to correct. I didn't realize, and later on I realized I made a mistake with the Lewis structure for HNO2 versus HNO3. So, when we have an acid like this, then the hydrogens are usually on the most electronegative atom. And so I put it on the nitrogen yesterday. I was thinking of nitro substituent. And so actually the correct Lewis structure for nitrous acid is like this. This would be the correct Lewis structure. So we have nitrous acid. Can you correct that? I put it on the nitrogen, so I have it for substituent purposes. But as an acid, it looks like this. And then for nitric acid, it looks like this. We're going to end up with some kind of formal charges here. In fact, we end up with formal charges, I think. There's no other way around it. We're going to end up with a positive formal charge here and a negative formal charge here, but overall it's a neutral. And so which of these two would you expect to be more acidic? And then we would think the one with the weaker bond. That's what we look for first, is a weaker bond. But in this case, both of these have the hydrogen-oxygen bond. If both of them have the hydrogen-oxygen bond, then what do we look for next? As far as acid strength goes. Well, there are different factors influencing acidity. The first thing we look for when we're looking at, differences in strength is, the bond. The weaker the bond, the easier it is to pluck off the proton. And so this is why, the example that we saw was HI versus HCl. The HI bond is much weaker. Therefore, HI is a stronger acid. All right, the next thing that we look for in terms of acidity is, anyone know? Polarity. We look for polarity. And so is there any difference in polarity here? And you might go, there's no difference in polarity because oxygen on the electronegativity scale is a 3.5, hydrogen is a 2.1. And so, when we look at delta En, the difference in electronegativity between hydrogen and oxygen, it's the same here. And then basically, if we look at the bonding here, it goes hydrogen, oxygen, nitrogen. This goes hydrogen, oxygen, nitrogen. And so is there a difference in the polarity here? And what we have to do is we have to look deeper into the structure. We can't just look at what it's directly bonded to here, because if we just look at the delta En and the delta En here, it seems as if they have the same polarity, which would be the same polarity as water, but it's different here in this case. It's different because of the nitrogen. These two nitrogens are quite a bit different here in terms of charge density. And how are they different? Because if you look at this, they're both nitrogens. This one, though, is going to have a negative formal, not negative, this oxygen has a negative formal charge. This one has a positive formal charge. And that's because we can't exceed an octet on nitrogen. So I'd like to form a double bond here. I have two double bonds and a single bond, but I can't do that. But right off, we see that a nitrogen with a positive charge versus nitrogen with a zero formal charge, those two are different. It's like this, Did I already ask you? I asked you what the electronegativity of fluorine, 4.0. But if I had fluoride, is it going to be the same electronegativity? No, it's going to be a different electronegativity. And so nitrogen versus a nitrogen plus has a different electronegativity. That's in terms of formal charge. But when we look at these types of structures, we also like to look at oxidation state, because oxidation state gives us insight into it as well. In fact, those are the two limits. If we look at, and sometimes the formal charge doesn't tell us this. In this case, it could tell us that, yeah, if there's a positive charge here, it's going to suck electron density away from this oxygen, which is going to make this more polar. Whereas if there's no charge here, then this is going to be less polar. In terms of oxidation states, what are the oxidation states here on nitrogen?
+3.
Okay, it would be 1, 2, +3. Okay. What's the oxidation state on this nitrogen? +5. The oxidation state on this nitrogen is +5. And so here we have a +3 nitrogen versus a +5 nitrogen. Which one is going to be more electronegative, a +3 or +5? More electronegative. Electronegativity is what? The definition of electronegativity. It's the ability to pull in electron density or attract electron density. And so +5 is going to be more electronegative. I mean, it's more positively charged, so it's going to suck more of the electron cloud towards it, which in turn is going to make oxygen more electronegative, which is going to suck more electron cloud from the hydrogen. And so it turns out, when we're looking at in terms of polarity, the polarity of this is going to be much more positive than this. And so we'll just draw different size deltas to indicate that. And so this is a much more polar hydrogen. And so this will be an easier, actually this will be much more attractive for a base. So if I have a base like hydroxide, hydroxide, which one do you think the hydroxide will attack preferentially? Will it attack the more positive hydrogen or the less positive hydrogen? It'll attack the more positive. And so the stronger acids, when we're doing the rankings for Bronsted acid-base reactions, we always pick the strongest acid to react with the strongest base. So if I had a mixture of nitrous acid and nitric acid, the nitric acid would react first, because that would be the target of a base like hydroxide or a base like water. And so in this case, it would be a polarity issue of making nitric acid a stronger acid than nitrous acid. The other thing we look at is the stability of the product. In this case, we look at the stability of the conjugate base. And so when we're thinking about bases, let's go over here to base strength for a moment and look at base strength. What makes a good base? Well, a good base is a good proton acceptor. A good base is a good electron pair donor. And so if we compare two bases, let's compare water versus hydroxide. Which one is going to be a better base, water or hydroxide? Both of them are going to donate a pair of electrons from the oxygen, but you'd expect hydroxide. Hydroxide would be a better base. Why? Why would it be more prone for accepting? Is it because it has 3 lone pairs versus 2 lone pairs, or is it because of the charge on the oxygen? Well, it's because of the charge on the oxygen. This has a full negative charge, whereas the oxygen in water only has a partial negative charge. And so full negative charge versus a partial negative charge, we'd expect a full negative charge to be. And in fact, that's what we're looking at. We're looking at this, partial or the full negative charge being attracted to the partial positive on the acid here. Okay. And so the higher the charge, the more reactive these are going to be. The stronger the base and the stronger the acid typically. So that's what we look at here. Okay, so we have hydroxide here, and then if we do this, let's say if we go versus something like this, FO. FO minus. Between these two, which one would you predict to be stronger? You'd say, well, both of these have a full negative charge on the oxygen. It's from the formal charge. But which of these two would you expect to be? You'd expect hydroxide to be stronger. Why? Well, both of these are very polar. Both of these are very polar because they're, full negative charge there. More polar in what way, though? I mean, All right, and so this would mean that oxygen would hold more electron density here, and then this. Okay, then the way I would think about it is a little bit different. The way I would think about it is a more concentrated negative charge on the active atom here, which is oxygen, the better the base. And so what's going to happen is fluorine, because fluorine's very high electronegativity, fluorine's going to pull the electron cloud from oxygen, okay, which is going to lessen the negative charge here. So as electron density is being pulled towards fluorine, that's going to be concentrated less on oxygen. Whereas here, oxygen is more electronegative, so it's pulling the electron cloud towards it, which is concentrating even more negative charge density on the oxygen. And so it turns out the degree of negative charge is more here than here, and that's because of this. We have a name for this, and this is the same thing here. You know, this electron cloud being pulled away towards the more electronegative atoms like this. That's called the inductive effect. And so here we're going to have, because of fluorine, some of the electron cloud is being pulled away. That's going to lessen the degree of the negative charge here. And so the conjugate base, the stability, you know, what's going to help in stability is what we call kind of delocalizing the negative charge. You know, delocalizing versus localizing. And so here the negative charge is more localized on the oxygen. Here it's a little bit delocalized because it's going to be pulled towards fluorine. And so the electron cloud is going to be distributed over a larger volume, where it's concentrated here. And so this would be like delocalized charge due to induction. Versus, let's look at this. If we look at hydroxide versus something like this. Then we might think, well, carbon and hydrogen have approximately the same electronegativity. You know, carbon's at 2.5, hydrogen is 2.1. So there's not a huge difference in electronegativity between carbon and hydrogen. They're very close. And so in that sense, there's not much, you know, maybe induction, except this carbon's a little different, right? This carbon is not a normal carbon, because this carbon would be more electron poor, more electron rich. In other words, what's the oxidation state on this carbon here? You know, normally when we're comparing carbon, like these two carbons, do these two carbons have the same electronegativity? What would you say? Yes? I mean, they're both carbons, so carbon has electronegativity 2.5. Would you expect both these carbons to have the same degree of electronegativity? No, because you know that electronegativity is going to depend on the charge on the carbon atom itself, and these two carbon atoms have different charge. Well, they don't, because they have the exact same formal charge. They have the exact same formal charge of 0. Both of these have a formal charge of 0. But it's not the formal charge I'm thinking about. What kind of charge am I thinking about? I'm thinking about, well, what are the two charges? Whenever we analyze a structure, what are the two charges we look for? Well, actually 3 charges that we look for. The 3 charges that we look for are, do you know what the 3 charges we look for when we're looking at a structure? When we look at a structure like water, we look for 3 charges. 1, formal charge. Are there any formal charges here? No formal charges. And then 2, what's the other charge we can look for? And so when I look at a structure like water, the formal charge is 0, all 0. Although the formal charge is all 0, At the opposite, what's the opposite of formal charge? Informal charge. Maybe they should have named it informal charge. No, that's not it. What's the opposite of formal charge?
Polarity?
No. Oxidation state. Oxidation state's the opposite. The oxidation state's +1, -2, +1. You know what polarity is? Do you think the charge is 0 on this oxygen? Do you think the charge is 0? That is, you know, hydrogen, the charge would be 0 if hydrogen and oxygen were in a tug of war and it was a tie. And therefore, the charge would be 0 if this electron cloud here, maybe I should have done this from the beginning. It looks like I have to review a lot more about bonding. But I'm going to skip it for the most part. The charge would be 0 if this electron cloud were what we call symmetric versus asymmetric, or in other words, nonpolar. Then it's 0. But do you think that electron cloud is symmetric? That is, if there's a tug of war, it's a tie. You think so? No, I don't think so. I don't think so because oxygen is more electronegative. So what happens is the electron cloud becomes like this. It becomes polarized towards oxygen. Now, if this charge were -2, that means this. If the charge were actually -2, do you think the charge on oxygen is -2? If the charge on oxygen were -2, then oxygen is completely stripped the electron cloud from hydrogen. That is, hydrogen has nothing now. Oxygen has all the electrons. Hydrogen's left with nothing. And here, then we get the charge. You know, this charge would be -2 because now oxygen has all 8 electrons. Hydrogen has nothing. This is +1, and this other hydrogen is +1. Do you think this is accurate? The water consists of the oxide ion and 2 hydrogen ions held together by ionic bonds. Do you think that's accurate? No. And so these are the two extremes. Oxidation state, is one extreme where the bonding is 100% ionic, and then the other extreme is formal charge where the bonding is 100% covalent. This is, if you want to go back and review this is back in chapter 10, is it? I don't remember. What is polarity? Well, the polarity is, you know, the charge is not going to be 0. It's not going to be -2. It's going to be somewhere in between 0 and -2. Do you know what that number is? We don't know what, it could be -1. We don't know what it's going to be. What the exact charge is. We can, you know, you can calculate using quantum mechanics. But rather than give it a number, we're just going to call it delta. This is delta minus. Delta symbolizes some number between 0 and -2. It's some partial charge. You know, not the full -2 charge that you'd expect on an oxygen, but some partial. And so that's what we have here. Over here, this is a full negative charge. This is probably get less than this here. For sure, it's less than a full -1, so it's some partial between probably 0 and -1. More like negative point something. Well, are these two carbons? These two carbons have exactly the same formal charge. Their oxidation states are different. What are the oxidation states? These two carbons here. +3 and -1. plus 3. Is that what other people got, or? Sounds like, this sounds like people are struggling with oxidation state. Is that correct? Yeah, struggling. How did you figure it out, Ian?
Well, I took the -2 charge you normally get with oxygen, multiplied by 2, and then added another negative to that, and then added 3 positive charges for the hydrogen. So I'm at -2. Again, 0, you need +3 and -1.
Okay. That's one way, I suspect. However, I'm worried that way isn't correct, because which one? You got +3 for this one? Or +3 for this one?
I guess it would be 1 times the oxidants.
Okay, and then you got -1 for this one?
Yeah.
How did you get this -1?
Well, just to make I guess the formal charge is -1, so I messed up, actually, because I balanced it to 0.
Okay, you balance these two to 0?
Yeah.
Okay, that's not the way, actually. That's not the way to do it. +3 is actually correct. You got this one right, but the way you did it is wrong. I could tell it's wrong because this one came out wrong. Otherwise, it'd be good. Anybody else? Megan, you remember? Or Kelly? What's that? Yeah, oxidation state on this carbon. -3? Yeah, -3 is correct. How did you come up with that, Kelly? Okay. So it takes 2 electrons from each hydrogen and then 1 from the carbon. So that's 1, 2, 3, 4, 5, 6, 7. So it has a total of 7 electrons. Then what did you do? It should have 4 valence electrons based on its position on the periodic table. We go over here. Group 14 or group 4 valence electrons. And then how did you come up with the -3? Well, in other words, it has 3 extra electrons. Each electron is negatively charged, so it's going to give it to you. Are you guys continuing in organic chemistry? If you're not continuing in organic, then you don't need to know this. You could just do oxidation states the normal way. If you're continuing in organic, then you would need to know this, because you need to know how the individual atoms, the electron density on the individual atoms, because these 2 carbons are totally different in terms of reactivity. So that's going to dictate how they react. Organic chemistry is a lot of carbon and a lot of this stuff, but you look at all the carbons formal charge is 0, so it doesn't look like there's any difference in reactivity, but there is difference in reactivity between these. But anyway, going back to this one, we would do the same kind of thing, oxygen versus carbon. Formal charge assumes 100% covalent. Oxidation state assumes 100% ionic, and then we treat the bonds as being ionic, so oxygen's the winner here. This is the way I would have done it. Oxygen's the winner, carbon versus carbon's a tie, so this carbon ends up with 1 electron. It ends up with 1 electron. It's supposed to have 4 valence electrons. It's going to get +3 for the missing. There's an imbalance between protons and electrons, and that imbalance between protons and electrons is what leads to the charge on an atom. So if it's still got the same number of protons, it's just missing 3 electrons, it's going to come out a net +3 charge. And so this is how we get this one.
Question?
And so this is +3. So what do you think about the electronegativities? Are these 2 carbons going to have the same degree of electronegativity? Are they going to have the same degree of reactivity? Are they going to have the same degree of et cetera, et cetera. No, these two carbons are quite a bit different. One of the things is this carbon has a positive charge. So if this carbon has a positive charge, that's going to help. That's going to help what we call delocalize the electron density on oxygen by pulling it in here. So the electron cloud is being pulled in towards this carbon because of its high positive charge. Now let's go. Oh, that's the same thing here. Didn't we see that here? The electron cloud is being pulled into fluorine, making it a weaker base, right? And so we'd expect this one to be a weaker base because of the what we call the inductive effect. This is the inductive effect, right? And so you'd expect, well, you know, which one's more electronegative, like a fluorine or a carbon with a +3? I'd still think maybe fluorine's going to be, and so maybe I would think this is going to be. I think in terms of ranking, this would be the strongest, and then this would be the next strongest, and then this would be the least strongest because of fluorine's high electronegativity. Does that make sense? But it turns out that this one is considerably weaker than this. In fact, this one is significantly weaker than this. And so maybe that carbon with the +3, it's not because of the carbon in the +3, and it's not because of the inductive effect. There's one more thing we have to consider here. When we're looking at delocalizing negative charge, we think in terms of inductive effect, one, and we think in terms of resonance delocalization. And so in terms of resonance delocalization, there are actually two resonance forms we could draw for this. And that negative charge, the negative formal charge, can move here to this oxygen here, like that. And so what happens here in resonance? You tell me, does the negative charge just move back and forth, resonating between the two oxygens? Is that how it works? Is that true or false? The negative charge resonates back and forth between the two oxygens. True or false?
False.
False is the correct answer. That's false. Well, tell me what's a more accurate picture of what's going on here. This would be back in chapter 9, 10, I think.
Isn't it that either form is equally valid at the other species is presented as?
No, I would think neither form is valid. Neither of these two forms is valid. Yeah.
Of the molecule delocalized electron structure?
Yeah, the molecule of the ion has a delocalized electron structure, which we call neither of these is valid. And so we have to do an ad hoc re-engineering of the structure, you know, after the fact, because we know that it doesn't resonate. We know that the bond doesn't, you know, for example, double bond shorter. So does the bond go longer, shorter, longer, shorter? No, the two bonds are exactly the same length. And the negative charge density on both oxygens is exactly the same. The negative charge density, and we call this structure, does anybody remember what this structure is called?
Pi bond?
Well, you're getting into, yeah, we're getting into pi bonds. I mean, what we're doing is we're delocalizing the pi bonding electron network, and the two ways we could delocalize that. We could do the thing with overlapping p orbitals, which is valence bond treatment, or we could do the thing with pi molecular orbitals, which is the M molecular orbital treatment of bonding. And so, actually, I'm going to do neither because I don't want to talk about bonding much more. I just want to say that this is called the hybrid, right? And so all we're going to do is we're going to come out with the resonance hybrid. And in other words, the pi bonding electrons here have been delocalized over both bonds like this. And so this is why we dot it here. The extra lone pair is delocalized over both. And so this is like water in a tub. You know, if I had a V-shaped tub, bathtub, water doesn't accumulate in one side of the V and not the other. And it doesn't, if you had a V-shaped tub like this, would the water be fluctuating back and forth like this? One side 2 feet, the other side 1 foot, and then back and forth. You know, it's a V-shaped tub, so if there's a connection, if there's a way to delocalize electrons here, the water's not going to be resonating back and forth, because if there's a connection between the two V's in a V-shaped tub, it's just going to reach the same level. In other words, the water is going to delocalize over the entire V-shaped tub, and so this is what we have here. This is called the resonance hybrid. In the resonance hybrid, what's the formal charge on each oxygen? What's the formal charge on each oxygen in the resonance hybrid? Actually, you know why I'm doing this here? I'm doing this because the organic chemistry professors have said that the students are too weak in terms of Lewis structures and in terms of this kind of stuff in analyzing the acid-base chemistry. So I thought, oh, okay, I better do more of this for organic chemistry. But for general,
They're each minus 1.5.
not 1.5. Try again. They're each minus 1? Not minus 1. Try again. Minus 2. Okay. No. Getting colder. Getting colder. You don't want to go minus 1 to minus 2. You're getting colder.
0.5.
Yeah, you got it. Minus 0.5. Each of these is minus 0.5. The way to do that is you got a minus charge distributed over 2 atoms, so just average it. Minus 1 over 2 atoms is minus 1/2. So each one gets a minus 0.5 here. The carbon, however, did the oxidation state on carbon change at all? No, the carbon's still at a +3. And so what's going to happen is we're going to get both. We're going to get resonance delocalization, which is going to drop the charge from minus 1 to minus 0.5. And then we're going to get the inductive effect, which is going to drop the charge even lower than minus 0.5, because this carbon's a +3. These oxygens are already, negative 0.5. So it makes, normally we think of oxygens being more electronegative, but and typically that's the case. However, this carbon's a +3, so in terms of the tug of war, carbon's going to be pulling much harder. Oxygen could still win, overall. We'd have to look at the numbers in more detail, but for sure carbon's going to put up a bigger fight and pull more electron density towards it. And so we got the inductive effect going and resonance delocalization. So that's what we look for. And so the more we can delocalize the negative charge, the more stable the base is. So hydroxide would be the most reactive here. And then followed by this one, the FO- ion, followed by acetate here. Acetate should be the weakest out of the three. And so, the more stable the product is, the better the driving force for the reaction. And so we can see. And so let's just do a couple of quick examples here for base strength. Oxide versus sulfide. We're going to look in terms of Bronsted, because what's the problem with looking in terms of Lewis? I'll tell you in just a second, but in terms of Bronsted, which one's going to be a stronger base? Oxide. Why oxide? Okay, you're talking about electronegativity. Oxygen has a higher electronegativity. Is that the reason why oxide is going to be a better base? So oxide, in terms of electronegativity, oxide really wants to get another electron to form the oxide extra minus ion. The oxide extra minus ion, the O3 minus ion, is really what we want. In terms of electronegativity, you have to get away from thinking, because in terms of electronegativity, electronegatives are going to be useful for certain things, but all we're looking at is positive and negative interactions. And so in this case, what is it trying to attract? The Bronsted base is trying to attract a positive hydrogen. And the more positive the hydrogen is, the more polar it is, the better, right? And so in terms of this, which one has a better ability to attract? You know, if you say it's because of electronegativity, then it wants to stay away from positive hydrogens, right? I mean, a base wants positive. A base does not want negative. And so in terms of, you should think of it as being maybe, what would be attracted to positive charges? What would you call that? Rather than calling electronegative, you call it electropositive. In organic chemistry, they have names for this kind of stuff. You know, the things that are attracted to positive charge are called nucleophiles. The things that are attracted to negative charge are called electrophiles. So all we're looking for is what's attracted. Is it going to be attracted to positive charge, nucleophiles, or is it going to be attracted to negative charge, electrophiles, in that sense? This is going to be attracted to positive charges, right? These are already negative, so this is going to attract. So which one's going to have a better time at attracting the positive hydrogen? So let's just take a hydrogen on water. Hydrogen in water has a partial positive charge. So which one? Well, you might say they're the same because both of these have a negative 2 charge. So if both of them have a negative 2 charge, maybe it's a tie, correct? And so maybe they're equal in terms of base strength. And we're going to try to pluck off this proton off water. And the answer is no, they aren't. It isn't a tie. One's better. For sure one's better. Do you know which one's better? Uh-huh.
Is it still oxide because it's smaller?
Yes, that's exactly it. It's oxide because it's smaller. You have a -2 charge here versus a -2 charge here. You know, oxide versus sulfide. And so oxide is going to be better because it has a higher negative charge density than sulfide. That's the reason why. Now we can't use this for Lewis because Lewis is a bit more complicated. What do you know about Lewis? The driving force for Lewis acid-base reactions. Okay, for Lewis acid-base reactions, it just depends on HSAB. HSAB stands for hard, soft, acid, base, and so it depends on what the acid is. In Bronsted, the acid is always the same. In Bronsted, we only have one acid, H. That's all. For Lewis, we have lots of different acids, not just H, but even the carbon can act as a Lewis acid, like in CO2. And so Lewis acid is much more complicated. And so sulfide's soft, oxide's hard. This is what we call soft, hard. And so sometimes sulfide is a much better base. Sulfide would be a much better base for soft acids because soft likes soft and hard likes hard. And so sometimes this is just reversed when we're dealing with Lewis acids and bases, so it's a bit more complicated. And so we're going to stick to Bronsted. For Bronsted, it's easy. And we don't have to worry about hard, soft acid-base theory. And so we'll just leave it at that because sometimes sulfide is a heck of a lot more reactive, especially with soft acids, than oxide. And oxide turns out to be weaker. But in Bronsned's sense, it's easy. Oxide's going to be better at plucking off the hydrogen. And so what all this means is there's going to be differences in acid strength, and differences in acid strength are going to lead to different pHs because what we're going to do is we're going to mix some acids and bases in water. And so the first part of this lab, we're just going to do some calculations. The second part of this lab is very quick and easy because it's just pH measurements. pH measurements do not take very long. Has anyone not used a pH meter? Okay. Just a few. All right. We'll go through. The pH measurements are pretty quick. So what we're going to do is we're going to anticipate what the pH is going to be first. And so let's take a look at the species that we're looking at in today's lab. What are the species? that we're going to be looking. We might not measure the pH of all those solutions. I don't know if it's necessary. But the first species we're going to look at is, I think, water. Right? We're going to look at DI water and distilled water. Does DI mean distilled? DI means deionized. Is deionized water and distilled water the same thing? No. Deionized, we use these ion exchange columns that exchange the ions in water with hydrogen ions and hydroxide. So it's a process. Which one's better, do you think? Distilled or deionized? Or are they equivalent? I think, as far as purity, distilled. Deionized is pretty good, it has high purity, but it's not pure enough for some applications. In fact, some of the things that I was doing in research, I had this big jug. I think it was a 5-gallon jug. This was when I was at UCLA. When I was at UCLA, I would put the 5-gallon jug and then go over to the psychology building, because in the basement of the psychology building is where they had the stills. And the deionized wasn't good enough. What they do is they take the deionized and then they distill it. They distill it once and then distill it twice. So it was called doubly distilled deionized water. And then hit it with UV after that, in case there's anything growing around there. And that's the water I'd use because I was doing sodium analysis. The problem with sodium analysis is everything contaminates sodium. The analysis. I mean, sodium's so ubiquitous; it's everywhere, and so that was very tough to do sodium analysis. This is a quantitative sodium analysis. I had to figure out how much. Not only was it there, I already knew it was there. Just figure how much was there. Couldn't use glass. Had to use plastic everything. Plastic beakers, plastic everything. It was a bit of a hassle. So anyway, we're going to measure the pH of this. What should the pH be? 7. 7.00. But did you know that does pH change with temperature? So what happens to the kinetic energy distribution curve here? If I increase the temperature, tell me what's going to happen to the kinetic energy distribution curve? Ian knows the name of this curve, this population versus kinetic energy, the Maxwell-Boltzmann or thermal Boltzmann distribution or Boltzmann distribution kind of thing. What happens if I increase the temperature? Remember, there's some kind of cutoff here. This cutoff is what did I call this cutoff yesterday? Well, I called this cutoff if a molecule is above this energy, it has enough energy that when it collides, bonds can be broken, bonds can be formed. So this is the minimum energy required for this reaction to occur. And at 25 degrees C, there's a certain population of here, which is like 4. Like something like 4 out of a billion or something. I forgot the exact number. You could calculate it, but I'm going to calculate right now. What's going to happen to the curve if I change the temperature? Let's say I increase the temperature. If it's colder or hotter, will that change the distribution? Uh-huh.
The opening of the bell becomes wider.
Yeah, okay. If it's hotter, this is what happens. If it's hotter, it becomes wider. It broadens the distribution because we're going to get even more high energy. If we get more high energy, what does that mean for the reaction? Well, if we have a greater population, that means we're going to generate more hydronium. If we generate more hydronium, what does that mean for the pH? The more hydronium, now it's an inverse kind of relationship. The more hydronium we generate, the lower the pH. You know? And so if the temperature goes up, I expect the pH to go down for pure water. For pure water, the pH should go down. What happens if the temperature goes down? Let's say we're colder. In fact, I think we're colder today than 25 degrees C. If we're colder than 25 degrees C, then the pH should go up. And so the pH should go up because the population is going to be less. And so this is what I expect. I expect this at 25 degrees C, the pH of pure water to be 7.00. At temperatures greater than 25 degrees C, I expect the pH to be less than 7. And at temperatures less than 25 degrees C, I expect the pH to be greater than 7. This results in a nightmare scenario. The nightmare scenario is, you know, your reference point for pH, pure waters, is always changing. And so, you know, you don't know what's neutral anymore. You know, let me ask you, at 15 degrees C, what is neutral? Where do we have the equal amounts of hydronium and hydroxide at 15 degrees C? What a hassle. This is a hassle. So we don't want to deal with this hassle. This is the reality of it. And so, but you know, we have sophisticated electronics nowadays. And the sophisticated electronics can do this. The sophisticated electronics will compensate for the temperature. So if the temperature goes up, the pH stays 7 for pure water. If the temperature goes down, the pH stays 7. Old style pH meters had a manual knob you had to turn. You turn this manual knob to adjust for the temperature. So to maintain that pure water has a pH of 7, you know, our reference point. That's old style. New style pH meters, built-in, usually built-in temperature compensators. So you don't have to do anything. You don't have to think at all about this because we don't worry about the temperature anymore. You know. But when you're doing your calculations, you have to worry about temperature because does K change with temperature? Yes, K changes with temperature. You know, and in fact, this is endothermic, so K would go up with temperature in this particular case. So for our calculations, we have to worry about temperature because that's going to impact K, it's going to impact our ice table, and it's going to impact the equilibrium. But when we're doing experimental pH measurements, we don't do that because we let the electronics take care of everything, and we're just going to say that the pH of water is 7 at all temperatures. Okay. But that's having the electronics compensate for this. And so, okay, with that, then we aren't worrying about the temperature. We're just going to measure our pHs. Now, when we measure our pHs, what we're going to do is we're going to try to predict. So we're going to predict that our pH meter should reach 7, no matter what the temperature is for this. The reality is it doesn't, unless it's freshly distilled. Freshly distilled water should read pH 7. If the water's been sitting out in the air for a while, it's going to read less than 7 because of CO2 contamination. All right, what's the next thing we're looking at? Sodium sulfate, or? We're on the hydrolysis lab, so we'll just go in order. Just flip to the table. Or is there a table? Or flip to the procedure and let's take a look. This lab has indicators. The indicators, we're going to skip the indicators. We're going to talk about indicators when we hit chapter 17. We're just going to measure the pHs using pH meter. It's going to be easier. Measuring pHs with indicators is very time consuming. And maybe we should do it, but
Is it sodium chloride?
48.
sodium chloride? Yeah, that's a sodium chloride is our first one. So what is the pH of a sodium chloride aqueous solution? And what's the molarity of this? 0.1?
Oh, yeah.
0.1 molar sodium chloride. So we're going to figure out the pH of that. Now, we think about, do sodium ions hydrolyze water? Do sodium ions hydrolyze water? No. Well, so what we say is sodium ions are neutral. How about chloride ions? Do chloride ions hydrolyze water? Chloride ions could potentially hydrolyze water, but these are too weak of a base to hydrolyze water. And so we call chloride neutral as well. This is neutral, but technically it's a base. You'll see it on the base chart. But it's too weak to hydrolyze water. And so if we have sodium chloride, the pH should be 7 and 0, because none of these will hydrolyze water and change the hydronium or the hydroxide concentration in water. And so they have like this. The group 1 cations are neutral. The anions of the strong bases are neutral. Chloride's not a good base. The same thing with nitrate. Nitrate is too weak to hydrolyze water. Nitrite, however, is not. Nitrite is a better base. Okay, what's next? After sodium chloride comes sodium carbonate. All right, now sodium carbonate consists of sodium ions. And so we're going to have 0.2 molar sodium ions, but you know, these are neutral. However, carbonate is not neutral. Not neutral. And so let me do carbonate for you. Carbonate is what we call a dibasic base. Dibasic. That means carbonate has the potential to take 2 hydrogens to form carbonic acid. And so if we have 0.1 molar carbonate, then we know carbonate's a base. Bases hydrolyze water. And so we'll have carbonate plus H2O liquid. This is going to go to what? If this is my base and this is my acid, then the acid water donates a proton, so we'll form bicarbonate. Even though it's a dibasic base, we only do 1 proton at a time in hydroxide. And so this is why carbonate's a base, because it hydrolyzes water to form hydroxide. Hydroxide will increase the pH of water, making it basic. And this is called a KB, or base hydrolysis. Base plus water is it. Now, there's a problem with this. Because of the conjugate relationships, we often have to calculate the KB. And it turns out that, let me just do this as an aside. It turns out that the Ka and the Kb for conjugate pairs, A and B have to be conjugate pairs, is equal to Kw. And so the K, this is take a this is generic acid. The generic acid I'm going to take is HA plus H2O. This is going to go to, well, it could go to, what is it going to go to? H3O plus and A minus. And so let's go ahead and do the Ka for this. It would be hydronium times the A minus divided by the HA. All right, now the conjugate base is A minus. A minus is a base. Base is hydrolyzed water. When base is hydrolyzed water, they don't produce hydronium, they produce HA and hydroxide. And so the Kb is just going to equal the HA times the hydroxide divided by the A minus. And so if we look at this, the A minus cancels, the HA cancels, and that leaves us with hydronium times hydroxide, which is Kw. And so this means that typically there aren't two charts. There's only one chart, the Ka chart, and then you calculate all the Kb's that you need. And so what we have here is we need the Kb for carbonate. The Kb for carbonate is going to equal Kw divided by the Ka for what? Acid. What is its conjugate acid? Well, its conjugate acid is going to be bicarbonate, and so we need the Ka for bicarbonate, or HCO3 minus, which we can look that up in a table. Kw, though. And so basically it's going to be this. We're going to have the initial, this is going to be 0.1 molar. Water is a liquid. This is going to be 0 molar and 0 molar. So we started off like this. And so why don't you go ahead and complete the ice table here, and I'll get the Ka value for bicarbonate now.